Hello everybody, and welcome back to another Engineering Statics lecture video. In this video we're going to be discussing the internal forces in beams. So it's going to be a natural continuation of our last videos where we talked about the internal forces of trusses. As we're going to see, it's going to be both very similar and very different, but don't worry, it's actually not too bad. Now before we begin, I just want to say I hope you guys are nice and happy. Enjoying what's going on so far, because I'm going to be honest with you guys. I like to be honest with the students. I'm not the kind of guy that hides it. Following this video, the next couple topics are going to be a little bit rough. Trusses, not too bad. Students usually seem to understand trusses very well. It's pretty simple and straightforward. What we're going to talk about today, also simple and straightforward. But the remaining topics of this course, it gets a little bit rough, and that's when the students kind of start hating me. I become the boogeyman of engineering statics. So hopefully you guys don't find it too bad and we have a nice kind of end to the semester. But that's for next video. In this video, we're still happy. We're still dealing with relatively easy topics. So let's just focus on the happiness for now. All right, let's jump in. So in this video, we're going to talk about the internal forces in beams. Now, internal forces is again something we have discussed before when it came to trusses. But how about what happens in beams? So let's look at our typical beam here. We know that we can apply external loads to beams. So in this case, I've applied 2 point loads P, and we've already talked about how these loads on our beams will create support reactions. So this is what we've done so far, and we've actually learned how to solve these support reactions, but we never really discussed what's happening inside of the beam. As you guys may guess, once I put a load on a beam, this load must actually be transferred inside of the beam over to the supports. So it's going to look something like this. Now, the question is, how exactly do we determine this? And what exactly is it? Well, we call these internal forces. Again, it's how we transfer external loads over to our supports. If you guys were to actually look at engineering as a whole, structural engineering specifically, our whole goal as structural engineers is to transfer the loads on our building down to the supports at the bottom. That's kind of the general goal of engineering. And then if we can say, all right, we've successfully transferred these to the foundation, which is kind of our supports, then we say, it's a geotechnical problem. They can deal with it from now. So that's kind of the goal as structural engineers. Now, why is this going to be an important topic? Well, as we're going to see, these internal forces actually govern our design. There's going to be 3 internal forces, and each one is going to play a very critical role. Now, as a structural engineer, this is my whole goal. What I do is I analyze the loads on a beam, and I determine their internal forces. And then I pick an adequate beam to resist each of these internal forces. Again, that's my whole goal as a structural engineer. If you do that, your building is mostly safe. There's other considerations we have to consider, but the main goal of structural engineering is to pick beams or columns or whatever you want to resist these internal forces. So they're actually very critical in design. So the question becomes, all right, they're very critical. How do we determine them? Well, for determinate systems, which we kind of talked about in trusses, it's actually going to be pretty easy and not too bad, especially since everything we deal with is elastic. In the real world, though, where things are plastic, which basically means things crack, things break, it becomes a little bit more difficult. So if that's the case, we actually do something called the finite element method. And this is actually another course that I teach, so a lot of you guys may actually know me from my finite element videos. It's a graduate topic. But the whole goal there is to find stresses inside a building. So in this particular case, I model a wall, and at the bottom it's fixed, and I'm applying a load to the top of the wall. So as we can see, there starts to become a nice stress distribution inside of the wall. Now this is again for very complex things that break, things that undergo fatigue, all that fun stuff. So we're not going to be dealing with the finite element method in this particular class, but I just want you guys to understand that internal forces is kind of the main game of structural engineering. We want to determine these internal forces and design our buildings against them. So as I mentioned, when we're talking about these internal forces, we've actually already dealt with them. They're actually nothing new to us. If we remember our trusses, and we had a truss, and I were to go, hey, snip, snip, and I were to cut through 3 of the members, we knew that we would create a free body diagram like this. And it turns out that F1, F2, and F3, those members that we cut, these are actually internal forces. Now, where things get a little bit different is, remember in trusses, all of our internal forces were either in tension or they were in compression. Basically, it was an axial force, and that was it. Well, as we're going to see in beams, it's going to be very similar, but there's actually additional forces that can happen in our beams. So let's talk about the internal forces of beams. As I just mentioned 2 seconds ago, beams carry multiple internal forces. Remember, trusses, it's just the one. It's that axial, either in compression or in tension. Beams carry multiple. So the first one out of these forces is actually going to be axial load. And it makes sense. If I were to take a truss member, like I said, I can have it in tension or I can have it in compression, and this can be the same thing for a beam. So if this was a steel beam, the beam can also be in tension or the beam can be in compression. And we already know that that internal force is simply going to be a force that is parallel to the member. So as we can see here, if I cut my member, the force is actually going to be parallel with the member. Now, we already said that for axial load, if it is positive, we say it's in tension, and if it's in compression, we say that it's actually negative. So that's going to be the first one. Again, comes right from trusses. You guys are saying, Clayton, easy peasy. Now, the one that you guys may have heard of, but we actually haven't discovered yet, is something called a shear force. All right, a shear force. And in design, this is the critical one. This is the force that kills people. And I sound dramatic saying that, but it's actually true. This right here is the killer. So if we were to look at shear force, this is going to be a force that is perpendicular to our member. So if this was my member and I were to cut it, my shear force is actually the vertical force. Now, shear force is important in beams because if I were to take my beam, the shear force is actually the force that would do something like this. Rip it right in half. And the reason why this is so deadly is because it happens in a matter of seconds. One of the things we do as engineers is we want to make sure not only is our building safe, but if somehow it were to fail, we want to make sure that it gives the occupants inside enough time to get out. So for instance, if my roof were to collapse right now, I would design it such a way that the roof would start to sag a lot. Because that, I would look up and say, oh, holy shit, the roof's coming down. I better get out. Shear doesn't give that warning time. If my building were to fail in shear, that roof would just break in half. I'd be dead right now. So it's one of those things that shear, it's a killer force, but it's one of the most important ones when we design. Now, shear doesn't really have a sign convention, and neither will the third one that we're going to talk about. So when we talk about shear, it's either going to just be positive shear or negative shear. And this is going to be very important. Remember, if in trusses, if we get a member that was negative, we just said, oh, it's in compression. Here for shear, if it's negative, we just say it's negative 10. It's negative 20. We don't try and convert it to something else. Now, the final force is going to be what we actually call a bending moment. I tricked you guys. I said force, but it's actually going to be a moment. So if I were to cut my beam, there's also going to be moment resistance inside of my beam. And again, this is going to be very important because one of the main things that beams fail with because they're so long is going to be bending. So this is actually going to be a moment that causes our body to bend. So if I were to take my beam right here, we know that we can bend it one of two ways. So what we actually do is we say that a positive moment creates a happy face and a sad moment, a negative moment creates a sad face. What do you mean? Well, if I look at my moments, right now I have them kind of curled upwards. And if I were to take my beam and curl it upwards, as we can see, we create a happy face. If I were to curl it downwards, we can see that we start to create a sad face. Now, this is the face all you guys probably have when you guys watch my videos. So it should be very relatable to you guys. So moments is actually what we want to design our building to fail. So if it were to fail, we would rather it fail by moment than by shear. Remember, shear, it just breaks right in half. What will happen if it fails by moment is the building will actually start to sag quite a bit. Again, you guys go, oh, better get the hell out of here. So those are the three internal forces in beams, all right? So it's actually not too bad. So what happens is when we want to determine these internal forces is going to be the exact same procedure as before where we simply cut our beam, but instead of just having an axial load like we did in trusses, we actually have to add all three of these forces that we have above. So let's say that we have our little beam here and we decide to go snip, snip right down the center of the beam. I don't know why I say snip, snip. It sounds like a circumcision. But snip, snip along the beam, and we cut it in half. So what happens when we cut it in half is we actually have to add all three of the forces. So the first one, of course, is the normal force, which we talked about, or the axial force. This is again something that you guys have seen a lot in trusses. We have the shear force, which again goes perpendicular to the member, and then we have a bending moment. So we essentially create three unknowns when we cut our beam. It's going to be shear, axial, as well as moment. Now, a couple things I want to mention. If we look at both sides, notice how they're equal and opposite. I have shear going up on one side, I have shear going down on the other side. Same magnitude, they'd cancel out. Same thing with normal forces. They're going opposite directions. And the same thing with moments. Now, this is going to lead me to the first thing that I really want you guys to remember. And that is this sign convention right here. Remember when we cut a truss, we always assumed tension. And if it was negative, we said, oh, it was compression, you know, kind of back and forth. When it comes to beams and when we cut it, there's no assumptions. There's no assumptions. If I were to cut my beam and use the left-hand side, so this side over here, I will always have my shear going downwards. I will never have my shear going upwards. This is one of those things that we call this beam sign convention, and it doesn't change. We always use this. Now, I have to put a little disclaimer here. For the American viewers, just double check and make sure this is what you guys do over in America. Because what I've noticed is a lot of the assignment questions I've seen from American universities, they have it opposite for moments. Now, this is actually very important because the idea of having a positive or negative moment, it's going to change things in reality. So in Canada, by using this sign convention here, we say that a positive moment does this, right? It makes a happy face. Now, this is important because if we take something like concrete and we were to bend it like this, we know that cracks are actually going to form on the bottom. So in Canada, if I were to say my moment, let's say positive 20, I automatically know in my head that my beam is doing this. Now, if this was opposite, like I think it might be in America, well, then what would happen is positive 20 would actually mean something like this. And in this case, the cracks appear at the top. So it's very important to know which moment is positive, which is negative. For those of you at the University of Alberta here, this is the sign convention we use. And again, what does it mean? Well, again, positive moment means this. Negative moment means it's going to do something like that. So again, that's the number one trick. Remember the sign convention. We're not assuming anymore. We always have a set sign convention when it comes to internal forces. Now, the first topic that we're really going to explore, which is kind of the nice, easy topic in this video, is internal forces at a point. All right, internal forces at a point. It starts to become a shit show next video because we talk about internal forces at every point. But for now, we're only going to concern ourselves with internal forces at one point. How do we calculate them? Well, as you guys may guess, we have our nice, sexy equations of equilibrium. So if I were to take my beam here, you know, it has a pin on the left, a roller on the right. And for some reason, I was very concerned about the internal forces at this particular point C. What I would do to solve it is simply go snip, snip at point C. And from there, I can create two free body diagrams. So if I were to look at the left-hand side where I have my pin, I know my internal forces are going to look something like this. Again, I didn't assume any directions here. These are the set internal forces from the previous page. The shear is going downwards, and the moment is always kind of pointed upwards, even though it's a rotation. If I were to look at the right-hand side, my internal forces are actually going to be different. And it's actually not too bad to memorize. Normal forces always pointing away. The moment, the arrow will always be at the top, even though it looks like they're both at the top. Remember, one's clockwise, the other's counterclockwise. The only thing that really gets students is that shear force, because typically, and I think that this is always ingrained into us, is we always like to analyze the left-hand side. I'm not too sure why. So if this is the case and we're analyzing the left, our shear is going downwards. But most students always assume that left is positive, so they put it upwards. But our shear is going downwards on the left. But here's the thing. We can analyze the left or the right-hand side. It's completely up to you guys. If you guys want to do this side and analyze the three forces, go ahead. If you guys are saying, left sucks, I'd rather go to the right side, go ahead. They're going to give you the exact same answer because it's equal and opposite. All right. So the first thing that we have to kind of discuss is this. If I were to look at these from kind of a step back, we have three internal forces, which means that we have three unknowns when we cut the beam. This means that those support reactions, AX, AY, or BY if you're doing the other side, they have to be known before we cut our beam. So when we're dealing with internal forces at a point, the first thing that we want to do is draw the free body diagram of the uncut beam and solve for those support conditions. All right, so you should know your support conditions before we actually cut the beam. Because now once we cut the beam and we expose those internal forces, we know what AX and AY are, so my only unknowns are going to be those internal forces. So once I decide where my cut is going to be, in this case it's going to be C, then I cut the beam and I draw another free body diagram. So this would be the free body diagram kind of on the right side over there. From there I can use my equilibrium equations yet again to determine those three internal forces. So it's actually fairly simple. It's the same thing as the method of sections in trusses. Remember, for the method of sections, we would determine the support reactions, cut the truss, and use equilibrium to solve for the internal forces. Same thing here. The only real difference is we have different internal forces. Trusses are just axial forces, and in beams we have the three. We have axial, shear, as well as moment. So just to really help kind of show you guys what's going on is, let's do a little example. So let's say that we have our beam here, and for some reason I really wanted those internal forces at point C. Well, the first step, of course, is draw the free body diagram of the uncut beam. So notice my beam right now, it's not cut, anything like that. I would say I have a pin over at A, so we have the two reaction forces. I have a roller at B, another reaction force. And then from here, I go right into solving the support conditions. And as we can see here, it's simply supported, nice and easy. If I were to do summation of force in the X, well, AX is going to be 0. If I were to take the moments about A, again, that's my personal tip or trick. Always take the moment about the pin. In this case, it doesn't help too much, but in other cases, it actually helps a lot. So personally, I always take the moment about the pin. I look at this equation. My only unknown is going to be By. I calculate By to be 50. So if you're in Canada, again, this is a force. So it'd be kilonewtons or newtons. In America, it would be, feet. No, not feet. What am I talking about? Feet. It would be pounds. And then now that we know By, we can take our summation of forces in the Y direction. And we were to say, all right, well, By was an unknown, but we now know what it is. So we're good to go. We can solve for AY. So again, this is something we talked about in a video, 4 videos ago. You guys are experts at this point. This will be no trouble. Now we can move on to the actual fun, which is determining those internal forces at a point. So the first step, of course, is draw a free body diagram of our cut beam. In this particular case, we know we want the internal forces at C. So I'm going to go snip, snip at C. I think if I say snip, snip enough times, you guys will say it in your head when you guys are doing these exams, which is always the best part. That moment trick that I did with my pencil where I kind of go up or down to figure out where the moment goes, I see students do that all the time in exams, and I don't know, it makes me smile like a proud Papa Bear, like watching all the kids learn from you. It's kind of fun. But so we cut it at C, and for this particular case, I'm going to analyze the left-hand side. You guys can analyze whatever side you guys want. It's going to be the same answer. Some of you guys might want to pick the other side because it has less forces. It doesn't have that 100 there. Again, it'll be the exact same answer. So if we look here, we say, all right, the first step into completing my free body diagram is showing all the forces. So in this case, AX and AY, well, we know what those are. They're 0, they're 50. If we look at our internal forces, we know that we have to add 3 of them because we cut a beam. So we're going to have our shear, moment, and our normal force. Again, notice if we're analyzing the left side, our shear is going downwards. The number one mistake I always see is students putting the shear going upwards. The shear goes downwards, something to always remember. Now we have all of our forces. The last thing that a true free body diagram needs is, of course, going to be the dimensions. So we know that we have 5 meters or 5 feet, and then we have 2.5 meters or 2.5 feet. At this point, we are good to go. We can jump into our equations of equilibrium to solve for these internal forces. If we look here, we have 3 equations, 3 unknowns, easy peasy. We can go right into the fun. So the first one, if I were to go summation of force in the X direction, well, we have our normal force and then our reaction force is 0. So we can conclude right away, we have no normal force. Nice and easy. Moving on to the next one, I can take the summation of forces in the Y direction. Now, if we look at AY, we know it's 50 going upwards, so I have 50. we look at the 100 that's applied kind of at the midspan, which is going downwards, so we go minus 100. And then our shear here, we have minus 50. This is why it's so critical to make sure you guys use the proper sign convention. If I had my shear going upwards, well, I'd get a different answer than what I'm going to get here. So in this case, we move the negative to the other side. We got 50 minus 100. We get that the shear is equal to negative 50. So this is going to be the first kind of key here that is different than trusses. In trusses, if we got negative 50, we would say, oh, this is actually 50 in compression. For shear, we leave it. You don't touch it. If you get negative 50, you don't change it to a positive. You say that the shear is negative 50, you're good to go. So shear, of course, is going to be units of force. If you're in Canada, kilonewtons. If you're in America, it's going to be pounds, something like that. And then the final internal force is going to be that moment. How do I do that? Well, I'm going to take the summation of moments about the cut. So there's going to be another little trick. You don't have to do this, but this is what I recommend. I always take my summation of moments about where I cut my beam. So in this case, I'm taking it about C. Now you guys may be saying, Clayton, why would you do that? Why is this so important? Well, again, it's not going to change anything. If you guys do moments 100% properly, you'll always get the correct answer no matter where you take it. The reason why I take it about the cut is because that's where my shear force acts. So I don't have to worry about shear force. And you guys may be saying, Clayton, you just calculated shear force. It's not unknown. You actually have it. Yes, that's true. But what happens if I accidentally calculated the shear force incorrectly? If I calculate my shear force incorrectly and I take my moment about A, well, then my calculation is going to use the incorrect shear force, and then my moment is going to be wrong. That's the reason why I take the moment about the cut, is we don't have to rely on previous calculations to get this one right. So let's say I somehow messed up my shear force, I still have a chance to get my moment correct because my shear force doesn't actually occur in this equation. So that's why I like to take the moment about the cut. In this case, if we do the math, our only unknown here is the moment. We get our moment to be 125. So in Canada, that could be kilonewton meters. If you're in America, that would be pound feet. But actually, a question for the Americans, is it pound feet or foot pound? I kind of see it mixed up depending on who I ask. So it's always one of the things that I've been curious about. So before we end this video, I just want to discuss two things with you guys. And this is going to be very important and why the next couple of videos are going to make your guys' life hell. First one is this. Let's look at that moment equation. One of the things that we had to do to take a moment is we had to specify distances. In this case, the distance to point C. If I wanted a different point, these distances are going to change. And if these distances change, well, then my moment at this particular, at this beam is going to change, the internal moment. And the same thing is going to happen with shear. If I were to calculate my shear on the left-hand side of that 100, you guys would actually find out it's equal to positive 50, not negative. So the reason why the rest of this course becomes more difficult is because right now we just looked at the internal forces at one point. In the next video, or I guess the next two videos, we're going to figure out a way to find these internal forces at every point along our beam. Now you guys may be saying, Clayton, why would we want to do that? That sounds terrible. It sounds like a lot of work. Well, the reason why is this. Again, as designers, we take these forces and we design against them. So if I were to look at point C here, and for my shear, I got negative 50. Do I know that this is the maximum shear my beam experiences? Well, the answer is actually, well, in this case, it's yes. But in some cases, no. The shear and the moment change throughout the length of the beam. So the reason why we want to analyze every point is we want to locate the point where the shear is maximum. Because if we find that point, that's the point we design against. And it's the same thing for moment. That 125 here, this is actually not the maximum moment on our beam. Surprising, but it's not the maximum moment on our beam. So one of the things that we do, again, is we analyze every point to try and determine where the maximum moment is. Because again, that's the value that we design against. So there's kind of the first thing. We want to analyze every point moving forward. The other thing that I always want to emphasize to you guys is just remember the sign convention. If you get shear as negative 50, leave it as negative 50. If you get your moment as negative 125, leave it as negative 125. You don't want to change the signs of shear and moment. It's only that axial force which can be compression or tension. For shear and moment, you keep it as negative. You don't try and do anything fun with it. And yeah, that's it for this video. So hopefully this was, again, a nice introduction into internal forces of beams. Again, last video where things are nice and happy and rainbows and statics. Everything else becomes a bit of a shit show for you guys. You guys really don't like the later topics. And the reason why is because, again, next lecture we're going to analyze the forces at every point. It becomes more work. Students don't like more work. After that, we talk about friction. Every student I've ever met hates friction. It doesn't matter if you're Canadian, American, anywhere else in the world. Every person hates friction for some reason. And then the topics after that are centroids and moments of inertia. And then you guys are saying, well, that sounds like ass. And it isn't too bad, but the reason why students hate it, it requires integration. Students don't like integration. You guys are thinking that's for the math nerds. That's not for me. Well, unfortunately, we have to do a little bit of integration in this course. So again, personally, this was the last happy lecture. Things get a little bit more rough from here on out, but if we stick together, I think we'll all be just fine. So hopefully this video helped you guys. I hope that the series actually in general has helped you guys. I know I'm rambling on a bit. Sorry for taking up all your time. But yeah, I just wanted to thank you guys and hope that you guys are doing well. The number one thing in engineering is your own mental health. So make sure that you guys are all doing well personally. If you guys are struggling with this and you guys need a break, take a break. I will personally help you. If you email me, I will personally help you catch up. I don't want to see anyone losing their mind. That's the worst thing that this can do to you guys. So yeah, that's all I have to say. Again, thank you guys all so much for watching this video. I really appreciate it. I will see you guys in the next lecture video.